Today we're looking at section 3.2, which gets into our very first shortcut formula for derivatives. So no longer are we going to have to use that algebraic derivative difference quotient in order to find the derivatives. In this section, we learn a very easy derivative technique called the power rule. So when we look at derivatives of power functions and later in the section, exponential functions, the first thing we need to talk about is a constant function. Most people don't think of a constant function as a power function, but it really is. If you have any constant, you can put any variable you want to right beside of it, as long as that variable is to the zero power. And then for that very reason, we're going to see here in a few minutes, the derivative of any constant is zero. You can also just think of that logically. We know that the derivative represents an instantaneous rate of change. Well, think about a constant function. The whole definition of a constant function is it never changes. If y is 5, then it is 5 forever and ever and ever. And so clearly, the derivative, its rate of change, is zero because it will never change. So any constant you have, derivative is zero. Up next, again, keeping with that theme of the derivative is the rate of change, what if I give you a linear function like y equals x? Then you can say its derivative, and notice the derivative notation I'm using here. I'm using f prime of x to denote the derivative. Here I'm using f prime of x to denote the derivative. The derivative of x is just 1. Now, I can further say the derivative of any linear function is simply its slope. And again, that needs to make intuitive sense to you, because since the derivative is an instantaneous rate of change, a linear function never changes its rate of change. If y equals 3x plus 5 goes up at a slope of 3 at one point, it always goes up with a slope of 3, so its derivative would be 3. Y equals x goes up with a slope at 1 at every single value of x. So I can say its derivative is always 1. Now let's look at a generalized formula for a derivative, and I want to prove it. So down on the bottom of the page, you'll see I have the derivative with respect to x of x to the n is n times x to the n minus 1. So if we want to take the derivative of any power of x, we simply bring the power down in front, multiply, and then decrease the power of the exponent by 1. But instead of just saying, hey, guys, that's what it is, I want to go up here and prove that to you. So whenever I'm looking at this, just as a precursor, I want to remind you of our Pascal's triangle, how we expand out, in this case, x plus h to the nth power. I can say, I know that x plus h squared would be x squared plus 2xh plus 1h squared. X plus h cubed would be x cubed plus 3x squared h plus 3xh squared plus 1h cubed. X plus h to the fourth. X to the fourth plus 4x cubed h plus 6x squared h squared plus 4xh cubed and plus 1h to the fourth. The main key concept I'm wanting you to see here is the second term's coefficient is always the same as the power on the group x plus h. Now that's going to play a part later on here. So if I want to prove the derivative of x to the n, then the only way I can prove anything is through the algebraic definition of a derivative. The derivative at any value of x on f of x as f prime of x is equal to the limit as h approaches 0 of the change in y over the change in x as that change in x gets infinitesimally small. H goes to 0. Well, okay. The change in the y values, f of x plus h minus f of x. What is f of x plus h in our problem? Well, it's going to become the group x plus h to the n, and then I have minus f of x, which is going to be minus x to the n. Okay, now, unlike where I have a given exact power, I don't know how to expand x plus h to any power of n. But here's what I do know. I do know that the first term of that expansion, x plus h to the n, it's going to be 1x to the n, guaranteed. what is the next term going to be? The next term is guaranteed to have a coefficient of n, and then it's going to be x to the one lower power and h to the first power. Now, the third term of the expansion, I really don't know exactly what the coefficient's going to be. I'm going to call it some arbitrary value b. And I know the power on x, it's going to be 2 less powers of n, and then I'll have h squared. Now, I put plus dot dot dot. That's just showing you that the rest of the terms will not matter. At this point, I don't expect you to understand why they don't matter. It'll become very obvious here in just a second. So all of this is my f of x plus h with the plus dot 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 saying the rest doesn't matter after the first 3 terms. And I subtract f of x, that's still my x to the n. As in all in these, as is always the case, the terms of f of x plus h and f of x always cancel. I cancel those out. And as is also always the case, all remaining terms have a factor of h. So I factor that h out of the remaining terms. Notice the gorgeousness of what happens inside of our limit when we do that. Okay, so remember, first term canceled out. What happens to the second term? Well, if you factor out an h, it's going to become n times x to the n minus 1 power. Well, what happens to the next term? Well, if you factor out an h, it's going to become plus b times x to the n minus 2 h to the first. Now, why do I not put any other terms? And why actually do I not even need the second term? Because remember, after we cancel out the h in the denominator with this factor of h that we we can cancel out with it, then you're going to take the limit as h approaches 0. So any terms that have a factor of h remaining in them, and please remember, every successive term is going to have a increasingly higher power of h. So they're all multiplied by 0, including this second term. So you'd say, well, okay, after I eliminate h, then I allow the limit as h to approach 0. So every single term in there, with the exception of the first term, all becomes 0, thus leaving us our derivative of f with respect to x is n times x to the n minus 1. And this stands for quod erat demonstratum, Latin for as has been demonstrated. Now, this shows us that if we have any polynomial power function of x, we just bring that exponent down in front and then decrease the exponent by 1. Now, this is my Leibniz notation down here. Anytime you see the prime notation, that's going to be Newton. The d dx is going to be our Leibniz. So, I mentioned that here on the next page. Whenever we start taking derivatives, we'll be needing to be accustomed to 2 different notations. You can use whichever notation you prefer, but you need to understand what someone's asking you if you see a different notation. So you can't just know one notation. Anytime you see prime, that obviously it means take the derivative. The prime notation is attributed to Sir Isaac Newton, one of the inventors of calculus. An independent inventor of calculus also, Wilhelm Gottfried Leibniz, who I actually think did a better job with his creation of calculus concepts, always used differential notation, and that it's always going to look like a fraction because he brought the idea over from slope, the change in y over the change in x. Well, the derivative is simply the infinitesimally small change in y over the infinitesimally small change in x for the instantaneous rate of change. So anytime you see that, that's Leibniz notation. And it looks like Leibniz, but it's pronounced Leibniz. It's a Leibniz. Now, for our, and you don't need to know this information for tests up here. I just wanted to provide that for you for just as an FYI. Now, as far as how to take derivatives, for the first problem I have here, I have f of x is equal to x to the 7th. I'm going ahead and using both notations for the derivative, whether I called it f prime of x or df dx. This stands for the derivative of f with respect to x. That's exactly the way you would read this. The derivative of f with respect to x is equal to, well, the power rule says bring the 7 down in front, then decrease the power by 1. Your derivative is 7x to the 6th. Now, students struggle on this next one because they'll want to say, well, why can't I say it's 1 over 3t squared? because it doesn't work that way. You're like, well, why not? In order for the power function to work, that variable has to be implied to be up in the numerator. That's the only way that that power rule is going to work. So a problem like this second one, you would have to rewrite from the very first step and say, well, 1 over t cubed, that's the same thing as t to the negative third power. Now it's written as a power function. Now I can take its derivative. G prime of t, or dg dt, is equal to, I'd bring the negative 3 down in front, decrease the power by 1. It's going to become negative 3t to the negative 4th. Now, I would always want you to put the final answer back in terms of the original expression. In other words, I don't want that negative exponent. Please also remember that negative exponent is only on the t. That 3 is not raised to a negative exponent. The negative 3 stays in the numerator. The t moves down to the denominator as a t to the 4th. I get my final answer, negative 3 over t to the 4th. Again, for this next one, before you take the derivative, you need to carefully go ahead and rewrite it. So you could say, well, 1 over the cube root of theta. First of all, I need you to remember, cube root of theta means theta to the 1/3 power. But now the fact that that's in the denominator means it's theta to the negative 1/3 power. So now I need to take the derivative of theta to the negative 1/3 power, and I can say, okay, I would call this derivative r prime of theta, or dr d theta, the derivative of r with respect to theta. Its derivative is going to be negative 1/3 comes down in front, times theta to the 1 last power. Well, negative 1/3 minus 1 is negative 4/3. So this would be my derivative answer. Now I just need to clean up that answer. I need to put my final answer back in radical form. I need to understand that this theta belongs in the denominator, and it's going to be the cube root of theta to the 4th in that denominator. So I write my final answer as negative 1 over 3 times the cube root of theta to the 4th. Gorgeous problem there. Now, what about if you have something like this? Can you have an irrational exponent and still use the power rule? Of course. So no problem at all. The fact that I have x to the 4 pi power, I still have a variable base, so this is still a power function. And I can say, well, the power function tells me I bring that exponent down in front, times the variable to the 1 less power, so it's going to be 4 pi times x to the 4 pi minus 1. And it's probably wise if I keep a parenthesis around that exponent to show that, but there's really no need to keep the parenthesis around the 4 pi. So I cleaned up my answer and said 4 pi times x to the 4 pi minus 1 power. And please notice your two derivative notations. Is it okay just to put a y or a prime beside a y to denote the derivative? Yeah, it's implied to be y prime of x just because your answer is in terms of x. But typically, whenever the original is written as y, you just say the derivative is y prime. In Newton that's a Newton notation. In the Leibniz notation, you just say, well, it's dy dx. Now, for my next one here, I'm asking you to take the derivative with respect to x of a constant times some function. And that's easy. The constant just gets carried along with it. You say, take the derivative of the function, multiply it by c. Now, I need you to see, that's what I've done in these problems. Technically, you could think of this as the constant 3 times the derivative, times the differentiable function, x to the 5th. You'd say, well, how do you take the derivative of x to the 5th? Be 5x to the 4th. Well, then the derivative of 3x to the 5th, you're just going to say it's 3 times 5x to the 4th. And what most people do, instead of even thinking of it that way, is you just say bring the exponent down, multiply by whatever's there. 3 times 5 is 15. Drop the exponent by 1. So our derivative of 3x to the 5th is going to be 15x to the 4th. Now, for this next one here, it's a little tricky. Well, not a little tricky. It's quite a bit tricky. I like it. I have 6 on the square root of 2x. So you would need to understand that that root of 2x needs to be broken apart. And the 6 root of 2 is understood to be the constant coefficient of the variable. And instead of putting the root of x, I know I need to use the power rule, so I need to understand that that x is really x to the 1/2 power. Please understand you could have written the original problem 6 times the root of 2 times the root of x. Since you can do that, you can call it 6 on the root of 2 times x to the 1/2. Now my power rule can take effect, and you would say, well, 1/2 comes down, multiplies this. You're going to get 3 on the root of 2. Then you decrease the exponent by 1, so it becomes x to the negative 1/2. Now, we can't stop there because you say, our original was in radical form and certainly didn't have negative exponents. So I say x to the negative 1/2 needs to be written as the square root of x in the denominator. And please, please, I would rather you keep the answer like this than if you think, well, should I rationalize that and call that 3 on the root of 2x over x? Nope. I think it looks better like this. If you insist on rationalizing, as long as you do it correctly, it's fine, but I would prefer you not to. And you'll see why in later classes. The actual answer, unrationalized, is easier to work with. Now, for the last one here, for part C, or last one on this page at least, I have 1 over 10x to the 10th. I had to rewrite that and understand that the constant coefficient is 1/10, and then x to the 10th in the denominator means I'm multiplying that 1/10 by x to the negative 10. I had to rewrite it this way in order to take the derivative, because the derivative now enables me to bring that exponent down in front and multiply. I would get 1 over 10 times negative 10, that gives me negative 1, and then drop the power, x to the negative 11. And then you could simplify that and say, well, this is just negative 1 over x to the positive 11th for your final answer. Now, all of this had to do with any time we had some constant multiplying a function. What if you have the summation or difference of several different differentiable functions? All I'm saying here for the sum difference rule, and it doesn't just apply to 2 terms, it could apply to 50 terms in there, any number of terms. You have a whole bunch of terms being added or subtracted. You just take the derivative of each individual term and keep the addition subtraction in between them. So now that becomes very clear in a problem like this. Every single one of these, I can just take the derivative easily by the power rule. So I'll just go in and say, well, the derivative, whether I call it y prime or dy dx, the first term, 6 times 10 is 60. Drop the power, x to the 9th, plus 4 times 3 is 12, x to the 3rd. Sorry, x to the 3rd becomes x to the 2nd. Drop the power. 2 times 7, I'm going to get a minus 14. Drop the power on x squared to give me x to the 1st. And then derivative of 5x, you need to think of that as 5x to the 1st. So you say, well, 1 times 5 is 5. Drop the power on the variable, it becomes x to the 0. And then we know the derivative of any constant is 0. So now, no problem there. And notice I didn't have to rewrite or anything. Every term just easy to take the derivative of. That's not the case for part B. Part B, as soon as you see variables in the denominator, you need to be thinking, I need to rewrite these before I start using the power rule. This first one is understood to be 3 times x to the negative 3rd. The second one, it's easier if you treat it as plus 1/2 x squared. And then the last one, minus 1/4, and I would call that x to the negative 6th. Now I can go in and take the derivative and say, okay, power rule should apply very fine now, whether I call this f prime of x or the derivative of f with respect to x. I know I say 3 times negative 3 is negative 9. Subtract 1 from this exponent, negative 9x to the 4th. The second term, 2 times 1/2 is 1. X to the 2 minus 1 power gives me x to the 1st. The next term, which is probably the trickiest for a lot of people, the negative 6 comes down and multiplies this negative 1/4. So I know a negative times a negative is a positive, and for now, just to show where it came from, I wrote that as 6/4. 6 times 1/4 is 6/4. Drop the exponent 1 by subtracting. Negative 6 minus 1 is negative 7. So I knew that this would not be a good final answer. I need to put it back in terms of positive exponents. My first term is negative 9x to the positive fourth. My next term, plus x, is fine. Then the last term, I reduce down the fraction to 3 over 2, and I can say plus 3 over 2x to the seventh in that denominator. Gorgeous problem there. Now, if there's anything better than that one, it's, hey, what if I put radicals in there where you have to understand the fractional exponents? That's good stuff. So one like part C here, you have g as a function of t. You say, gee, I think we can do this. But before you do, you have to go in and rewrite the radicals as fractional exponents. This first one is going to be 20 t to the 2/5. Remember, power divided by index. This next one is going to be 4t to the 4/3. And the last one, trickiest one, all of that is under the 4th root. I can leave the 6 under the 4th root. I can say minus the 4th root of 6, but then I need to understand that that 4th root of t means that's t to the 1/4 power. So now I can say, okay, I've got it all in there to where I should be able to use the power rule. So g prime of t, or the derivative of g with respect to t, is equal to, where did this 8 come from? 2/5 times 20. That's going to give me, yeah. It's 8. 2 times 20 is 40, divided by 5 is 8. I started to think I was wrong, but I was wrong. I was right. So I get the 2/5 times 20 is 8. And then t to the 2/5 minus 1 power is to the negative 3/5 power. The second term here, 4/3 times 4. I get 16/3. And then t to the 4/3 minus 1 power, I get the 1/3 there. Up next, 1/4 times the 4th root of 6. I'll just call that the 4th root of 6 over 4. Again, I'm keeping that minus sign I had out in front. And now I need to subtract 1 from that exponent. Well, 1/4 minus 4/4 gives me negative 3/4. Now, I know that all three of these are correct. I just need to write them back in radical form. So this first one, the fact that I have a negative exponent means that that t belongs in the denominator. It's going to be the 5th root of t cubed in the denominator. So I have 8 over the 5th root of t cubed. My next term here, I have 16/3, and this t belongs in the numerator along with the 16. It's just going to be the cube root of t to the 1st in the numerator. A little sloppy there. Had to use whiteout and it didn't write over it well. The last one here, I have the 4th root of 6 over 4. And then this t to the negative 3/4 power. I can say, well, that t belongs in the denominator along with the 4, and it's going to be the 4th root of t cubed in that denominator. So you see the 4th root of t cubed down there along multiplying the 4. Whenever we had the problems before this section, we had several in which we had to find the equation of the tangent line to a curve at a particular point. You're still going to see problems like that pop up. So that's why I say, of course, the old problems pop up where we have to find equations of a tangent line, but now it's super easy to find them. Because rather than having to go into that limit definition of a derivative to find the derivative of this at a particular point, you just say, hey, I know my power rule. So if I want to know the tangent line to this curve at its y-intercept, first of all, my point, the y-intercept is when x is 0. When x is 0, though we know the y value is just going to be 12. So our point is the ordered pair 0, 12. My slope is just going to be the derivative evaluated at the x point of interest, which is 0. So I can say, well, okay, here's my function. Power rule says its derivative is going to be 4 minus 2x. Now, the derivative at 0 is going to give me my slope at the point of interest. So I can say, well, if I plug a 0 into that, I'm just going to get a slope of 4. So now I know my slope is 4, my point is the ordered pair 0, 2. I plug that information into your point slope formula, and you get y minus 12 is equal to 4 times x minus 0. That's just going to be y is equal to 4x, and then we move over the 12 for plus 12. Final answer for the equation of the tangent line to that curve at the ordered pair 0, 12. Now, I like this next problem much more so. Let's say I ask you, instead of just asking you for an equation of a tangent line, I say, I want you to tell me when the tangent line is going to have a particular slope. So in this case, I'm asking you to determine the values of x for the slope, and that should be of the tangent line to the graph of g of x is equal to -9. So whenever you're thinking about what this means, that's what I put, so dot, dot, dot. We need to find the values of x where the derivative g prime of x is equal to -9. Anytime it's saying find when the slope of the tangent line is -9, it might as well say find when the derivative is -9, because the slope of the tangent line is only going to be -9 if the derivative is equal to -9. So I can say, okay, need to take the derivative, try to set it equal to -9. Here's my function g of x. Its derivative, power rule, I bring the 3 down, times x to the second. 2 times 3 is 6, times x to the first. Derivative of 5 is 0. So my derivative is this 3x squared minus 6x. Now, when I was working with that, I'm just trying to think about how I would show it would equal -9. What I decided to do, rather than just try to set it equal to -9, I didn't want to use quadratic formula or anything like that. Instead, what I went ahead and did is I completed the square on it. So I factored a 3 out of this group, and I said, okay, if I can factor a 3 out of that, then it becomes x squared minus 2x. Now, what I wanted to do is create a perfect square trinomial in there. And I said, well, perfect square trinomial always has a perfect square constant that is always b divided by 2 quantity squared. Well, 2 divided by 2 is 1, 1 squared is 1. I can create a perfect square trinomial if I add a 1. So in red, just to show I did it later, I added a 1 there. But as you know, you can't go in and just add terms to problems wherever you want. So I had to make up for that. If I added a 1 on the inside, and I need to understand this 1 is being multiplied by 3, well, then I can make up for that by subtracting 1 on the outside and multiplying it by 3. So in other words, I'm subtracting 3 out there. So g prime of x, the whole point for doing this was I could say, now I can call g prime of x 3 times the group x minus 1 squared minus 3. Now, if you think about that this is just a parabola that's been shifted to the right 1 unit and down 3 units and then stretched by a factor of 3. Okay, how does that help? Oh, it helps tremendously, because we're trying to show that g prime of x is -9. This shows that it can't equal -9. So think about this with me. We know that 3 is multiplying some number that is the very minimum 0 when x is 1. Other than that, it's a positive number because it's a number squared. So this is 3 times the lowest it could ever be, a 0 minus 3. So g prime of x is going to have a range that starts at -3 when x is 1. After that, it's going to go up on both sides. So I know that g prime of x could never equal -9. All right. Then that tells me, to answer this question, there are no values of x where the tangent line has a slope of -9. And again, that's because the derivative can't equal -9. Good problem. Now, just to finish up this section, the last thing this section talks about is exponential functions. And whether I give you the Leibniz notation for the derivative with respect to x of e to the x is e to the x, or the Newton notation, e to the x prime, that's saying the derivative of it's e to the x. So exponential functions are the only functions who have themselves in their derivative. So you just say, it doesn't change anything. Please don't get this confused with a power rule. Power rules are when you have variable bases, constant exponents. Exponential functions, constant bases, variable exponents. And we're saying their derivative is just themselves. So derivative of e to the x is e to the x. Please do not be the student that says, well, is the derivative of e to the x times e to the x minus 1? No, that would be horrible. Doesn't work. Power rule only applies to power functions, not exponential functions. So now, just to make sure that you got that straight, I put a problem that involves both power functions and exponential functions in it. And you say, okay, no problem. The third term here needs to be rewritten. I can say this is just x to the fifth minus e to the x. This last term is minus x to the negative fifth power. Now, when I take the derivative, the first term is going to become 5x to the fourth when I subtract 1 from that exponent. Derivative of any exponential function is that exponential function. It does not change. And then the derivative of x to the negative fifth, I can say negative 5 comes down, multiplies that minus, it's going to become plus 5, and then x to the negative 6, subtract 1 from the exponent. The first two terms are absolutely fine notation. The last term needs to be rewritten as 5 over x to the 6 because you never want to have negative exponents in your answer. Now, if I do one more here, a person might think, well, hey, the derivative of g of x is going to be the same thing as g of x because everything in there is an exponential. There's nothing wrong with that statement. Everything in there is an exponential, but not everything in there is an exponential function. Please notice e to the 4 pi, constant raised to a constant. The square root of e, that's a constant raised to a 1/2 power. Again, a constant to a constant. But now the last term, minus e, constant base, variable exponent. There is only one exponential function in this problem. And please remember, the derivative of any constant is 0. So I can say, well, okay, the derivative of the first two terms, 0 and 0. The last term, derivative of any exponential function, is just that exponential function. It doesn't change. So we would get our very easy final answer as long as you understand that those two have a derivative of 0 since they're just constants. Now, something I really want to drive home here, and I hopefully I've already done this on this page, but each different class of functions that we're going to come across are going to have their own distinctive derivative rules. We've seen power functions and we've seen exponential functions in this case. In the next section, we're going to be looking at what happens when we have functions that are being multiplied that you can't just carry out the multiplication. You can't just simply take the derivative of the first one and the derivative of the second one. We're going to have what's called a product rule, and we're going to have a quotient rule for whenever we have terms divided by terms. Then we're going to have rules for our trig functions. They all have their own separate functions. So as you look at each of these problems, you've got to look at what each term is and say, oh, that's a power function, that's an exponential function, and then whatever others that we get to later. But they all have their own derivative rules. So what we should know for now is if you see a power function like x to the nth power, we know that the way that we take the derivative is we bring that power down in front and then raise it to 1 less power. The answer is still a power function, just 1 degree less. And then exponential functions are always going to stay the same. They have their own exponential derivatives. All right, guys, until section 3.3. Hope you're doing well, and please let me know if you have any questions. Be glad to help at any time.